So ester hydrolysis is a reaction that is essentially the opposite of ester formation. Now, what makes ester hydrolysis a little bit different from ester formation is we learned the most common way to make an ester is an acid-catalyzed Fischer esterification, where we use an alcohol and a carboxylic acid with an acid catalyst to form an ester. Ester hydrolysis, on the other hand, we can do under two different sets of conditions. Acidic, and when we see acidic conditions, we're going to see that this is the exact reverse of the Fischer esterification. Now, the unfortunate side of this reaction is that means that just like with the Fischer esterification itself, equilibrium is going to be a major factor in this reaction, and there's really no way to avoid it. So we'll talk about that one first briefly. After that, we'll talk about the more common way of doing an ester hydrolysis, which is under basic conditions. And while there's certainly an equilibrium issue to worry about in that reaction, based on the steps in the mechanism, it largely takes care of itself. And so we don't have to be as concerned with some of the factors that affect equilibrium as we needed to be under acidic conditions. So we're going to start here with acidic conditions. And if you think back to the Fischer esterification and think back to those steps, you're going to see those exact same steps, just in reverse. So we start, again, because we're going to need to add a nucleophile to the ester. And since we're under acidic conditions, our nucleophile, neutral compound, water, not such a great nucleophile. So that's what our acid catalyst is going to do. Is again, it's going to activate our carbonyl so that our not so great nucleophile water can attack. From here, we can get a proton transfer from what was the water that attacked over to the group that needs to leave, the methoxy or the O-methyl group. Although since we're under acidic conditions, it won't be a methoxy group when it leaves, but methanol. Now, lone pair on oxygen adds in. We kick out our leaving group. And finally, we lose a proton. We're regenerating our acid catalyst to form our carboxylic acid. Just like the Fischer esterification, which is the reverse process of this reaction, equilibrium is an issue. Typically, the easiest way to overcome this process is by adding an abundance of water. Same way that for the forward reaction, the esterification, we added an abundance of the alcohol to take advantage of Le Chatelier's principle and push the reaction in one direction. Here we add an abundance of water to do the opposite. But as we said, the basic conditions are more commonly used, a little bit easier to control. So under basic conditions, we're using hydroxide. And since we have hydroxide, which is certainly a stronger nucleophile than water, we don't need to activate the carbonyl. The hydroxide will add directly. And then O- can add its lone pair back in to our tetrahedral intermediate and kick out what you're probably going to say is a bad leaving group, ethoxide. And if you said that that was a bad leaving group, you'd be right. So why is it that the reaction's still able to work? Well, it turns out that that step doesn't work all that well. The equilibrium isn't terrific. It wants to reverse itself back to the starting materials. But if any of it gets through, we get the two compounds pictured below as our next intermediate. And there's a pretty significant pKa difference between an alcohol and a carboxylic acid. A carboxylic acid typically has a pKa of down around 4 or 5, whereas an alcohol might have a pKa of 15, maybe even as high as 18 or 20. And so if any of that's formed, it's immediately going to exchange proton. And because the pKa difference is so significant between the carboxylic acid and an alcohol, in theory, of course, we should draw that step as an equilibrium step. But the equilibrium lies so strongly to one side of this reaction that we can essentially show it as a one-way reaction. And so that means that any of the carboxylic acid that forms from loss of this bad leaving group, it immediately gets pulled out of that equilibrium. And that's going to allow us to drive the entire equilibrium of the hydrolysis forward. So again, even though we have a step in the middle that doesn't look so good, we can take advantage of equilibrium to drive the reaction forward. Final step is that you would quench this with acid. And you get your carboxylic acid. Now, one pretty interesting, neat application of ester hydrolysis, it even gets into why this reaction sometimes is referred to by another name, which is saponification. It involves a compound that actually has 3 esters. So we have this, what's essentially a triol that gets added to 3 different carboxylic acids, and each one of them has a long chain. And you may be familiar with compounds like this, but this is a triglyceride. And if you take a triglyceride and treat it with hydroxide, you may have to heat it up as well. You'll get hydroxide to add in 3 separate reactions to each of these carbonyls. And as a result, you'll cause each of those those carbon-oxygen bonds to break, and you'll form this byproduct, glycerol, which has a number of uses. It can be used to make nitroglycerin. It also is used in a lot of skincare products. But even more importantly, you end up with the carboxylate salt of whatever that long chain was from the triglyceride. And that compound, should be one that's pretty familiar to us, even if we don't recognize it by structure, but it's through this reaction that we make soap.